introduction into. So, so hi everyone. My name is Guillaume. I just finished my PhD as part of a collaboration between EPFL and IBM Research in Zurich. And today I'd like to highlight some of the work we've been doing in the direction of graph representation learning in computational pathology. So before starting, I'd like to acknowledge all the people that contributed to this project. So my colleagues from IBM, EPFL, and ETH. So we know that two of the main, I want to highlight two of the main challenges in computational pathology. So the first one is that histology images can be several gigabytes in size, which of course brings computational bottlenecks and hardware limitations. Just to give you an idea, a whole slide image at the highest resolution can be as big as 40,000 times larger than an ImageNet sample that is typically used to train deep learning systems. And the second big challenge is understanding histology images require domain-specific expertise that only pathologists can provide and us computer scientists don't really understand, which of course makes it hard to get data and to get annotations to develop methods. And even when we get annotations, we know that they are high in terms of variability. And in addition to that, it means that the integration of computer-aided diagnosis tools in the pathology workflow needs to be, or at least to some extent, needs to be transparent and explainable. So this is an overview of the main publications we've been doing over the past 2 years at IBM to address these challenges. So first, we have worked on the scalability. Again, deep learning was developed on small images, so we had to propose methods that can scale to much larger inputs. The first point. The second is we worked on explainability to interpret predictions of deep learning systems, and we did that by incorporating prior knowledge into our systems. Then the third one is that we worked on methods that are annotation efficient, or in other words, methods where we try to minimize the amount of labels, the amount of annotation that we need to train the system. And finally, we've worked on developing open source libraries that can be reused by the community along with public data sets that people can use to benchmark their approaches, right? So I don't know if you saw, but from the titles of all these papers, what is at the core of all these methods is a graph-based representation where the nodes of the graph will encode entities, biological entities, and the edges will encode relations between these entities. So a natural choice is to, for instance, use nuclei as node in the graph, but we can also use different tissue regions, or we can even use glands, or we can simplify and just encode it as patches. And then the graph topology, so basically the edges can be defined by enforcing some kind of locality principle in our system. For instance, we proposed HACT, which is a hierarchical cell-to-tissue representation that is based on a cell graph and on a tissue graph to comprehensively represent our histology image. And on top of that, we have proposed a novel neural network to map HACT to breast tumor subtypes. And if we do that, we can evaluate our methods, and we created our own data set of breast tumor regions called BRACs that is now publicly available, and you can start using if you want. And what we showed is HACTNet can outperform other graph-based methods and standalone CNNs with a performance of over 60% F1 score over 7 classes that are ranging from benign to invasive. And its data set will also include atypical cases like FEA and 88, which is a common thing to do in computational pathology. And when compared to external pathologists, we observe that their inter-agreement is often below 60, which is here proving the power of HACTNet and AI. So now we can look at cell graph models where the nodes represent nuclei. And again, as our input graph is biologically meaningful, we can define measurable nuclei level concepts to characterize them and compare it with our prior knowledge and prior understanding of the task, which is why we claim that our input is more interpretable. So the idea is the following. We start by applying a feature attribution method to highlight the regions where the algorithm is focusing on. The simplest and most popular one is, of course, to use GradCam, but alternative methods exist. And we obtain something like this here, where important nuclei are shown in red and less important ones in blue. And we also want to go one step further to understand if it is expected that the AI model is focusing on this set of nuclei to make its prediction. And here we are leveraging our prior pathological knowledge. For instance, we know, or like we expect, that cancerous nuclei to be larger than the benign ones. So we can simply compare them by constructing the distribution of the nuclei size over a set of samples, and we obtain something like this. And like we clearly see that like the important nuclei for the malignant samples are on average larger than the benign ones, which is again matching our prior knowledge. So this was for the interpretability. And what we have discussed so far focuses on classification, which is something important, of course, but not necessarily the best to assist pathological focus during diagnosis. So we have proposed a model that can jointly perform whole slide classification. So here it's Gleason grading and whole slide segmentation. That is basically assigning a Gleason score to each pixel of the whole slide. And as I said in the beginning, getting annotations is really hard. So we want to do that by only using whole slide level labels for the training. So this is an overview of our method, where the beginning story is the same. We transform our image into a graph. So here, tissue graph. Then we have a classification head to predict the cancer grade. So here, the primary and secondary Gleason grades, Gleason scores. And from there, we can derive node level, so the labels that are obtained here again using a feature attribution method. And finally, we are training a no classification head using these pseudo labels. And from there, we can trivially obtain a nice pixel level segmentation of the input along with this classification. So this is what we obtain. So the ground truth is shown here on the left column, and the predictions are here, the right column. And what we see is that this approach offers an interesting way to highlight cancerous regions directly at pixel level. So this should give you an overview of the work. And again, like developing all these steps from scratch takes time. And as the number of papers using graphs is increasing, we have decided to build our own Python library called histocartography to start working with graphs. And you can freely use it, it's open source, and you can find the GitHub link here. We're also organizing a challenge at ISB this year called Bright for whole slide classification of breast biopsies. So you can still register to the challenge and participate. And with this, I'd like to thank you for your attention. Thanks.